Yeah, today we will actually see um the, the continuation of yesterday's tutorial discussion. We couldn't actually finish it. That's why I actually thought of having a half-hour session, and we can actually finish it off. Yeah. So yesterday we were actually seeing the fin problem. Okay. So in which we are actually seeing finned passages, right? So we are actually seeing that if we are actually having a passage like this, how the heat transfer coefficients are actually going to be. So we said that this one is actually the special situation. Again, I'm actually sorry, I don't have my writing part with me. So what we actually said is uh, highlight is also not there. Let's see. Yeah. So what we actually said is this is actually the fin. Okay. So instead of a free end, we can see that it is actually both the ends are actually attached to some materials which is actually at a constant temperatures. Okay. So therefore, we actually said that the basic equations are actually going to be the same only. Okay. So therefore, the solution will be actually taken the form C1 e raised to mx or C2 e raised to minus mx. Or from our discussion, we actually wrote it in terms of sin HMS and cos HMX. Okay. So you can actually write it in that way also. Okay. Yeah. So we actually derived everything based on cos hyperbolic function cos HMX and sin HMX. Okay, so same way you can actually write. Only that here we are actually saying that at x is equal to 0, the temperature is T0 and x is equal to L, temperature is equal to TL. Okay, so the x starts from top to bottom. So if you are actually doing that, then you can actually see that we are actually deriving it, and you can see that if you are actually writing in terms of sin HML and cos HML, then it is actually similar to whatever we actually derived for a constant temperature condition. Okay, at the end we actually taken one condition where the prescribed temperature condition. So in this case also, for in this problem also, we are actually deriving whatever is actually we actually derived in that particular condition. Okay, so even though we can see that even though it is actually say not the regular fins in the conventional manner, so here again you can actually see that with the condition prescribed temperature condition, it is actually given the same whatever we actually discussed. So that is actually the first part. Obtain an expression for the fin with this configuration. Okay, and also it is actually asked what is actually the heat transfer rates at QF0 and QFF. Okay, so that one you can actually given by the equation Q of so is equal to minus K AC into dt by dx at x is equal to 0. Okay, so you have to actually do the derivation. So here you can actually see that yeah. So that also I think we have actually done, right. Yeah. So but we have actually done only for dt by dx at x is equal to 0. Yeah, dt by dx we have actually found, right. So dt by dx we have actually found. So from the dt by dx for a heat transfer rate, for the heat transfer rate at x is equal to 0, you have to put x is equal to 0, and heat transfer rate from the bottom surface, you have to actually write what is actually x is equal to L. Okay. Yeah. So one more thing is that in our regular fin, what we actually was saying is that so heat is actually reducing continuously, and the heat transfer was always from the base surface to the end surface. Okay, but since we are actually saying that in our this particular configuration we are actually given to two surfaces, the both ends of the fin are actually attached to both surfaces. Here you can actually see that heat transfer is actually going to the fin structure, going to the fin structure or the intermediate structure from the top surface as well as the bottom surface. Okay, it is not that heat is always reducing in one direction. It is not like that. It is actually heat is actually being transferred from the bottom surface to the fin structure from the bottom surface as well as from the top surface. Okay, So therefore, you can actually see that, but that actually doesn't matter our equation actually. Okay, so you have to always go with our particular equations. Okay, so that the negative signs, whatever we are actually talking about, it will actually taken care of. Okay, so because the equations will be automatically taken care of everywhere. So only that you have to actually put at x is equal to into the equation minus k a into cross section dt by dx at x is equal to 0 and x is equal to l. Okay, we have actually found during our discussion itself, we have actually found what is actually the dt by dx. So into this, you have to put x is equal to 0 or x is equal to l. So if you are actually doing that, then you are actually getting what is actually the heat transfer from both the ends. Okay, yeah. So obtain the expression for the fin heat transfer rates QF0 and QFL in terms of base temperatures T0 and T. Okay, so that actually concludes the first part. So is that clear? I haven't gone through the question again because we were actually discussing it yesterday. Is that clear, or does anyone want me to discuss it again? Is it clear?
Yes, sir.
Yeah. Okay. Yeah. So the second part is that in a specific application, a stack that is 200 millimeter wide and 100 millimeter deep consists of 50 fins, each of length 12 mm. Uh, the entire stack is made from aluminium, which is everywhere 1 mm thick. Okay. So if the temperature limitations associated with electrical components joined to opposite plates dictates allowable maximum allowable plate temperature of T0 400 Kelvin, okay, and TL 350 Kelvin. What are the corresponding maximum power dissipations if H is equal to 150 and T is equal to 30 Kelvin? Okay, so what is actually given is it is actually given the dimensions. Okay, so all the dimensions of the fins. Okay, and also it is actually given what is actually T0 and what is actually TL, and also it is given what is actually the heat transfer coefficient and the temperature, ambient temperature. So all the criteria are actually given to us. So from here we need to actually see what is actually the basic uh, heat what is actually the basic heat flux conditions, so that we actually already seen, right? So what is actually the basic heat flux condition? So into that we have to actually put these parameters. Okay, so here it is actually given the total heat flux. uh, yeah, so total heat flux, it is actually given QFO and QFL, right? So that is what actually being asked, what are actually the corresponding maximum power dissipations. So what is actually the total power dissipated from the surface? So what is actually given is yeah. So first we have to actually find M. So M is equal to HP by KAC. H it is given. Perimeter also we can actually find from whatever the dimensions it is actually given. Okay, and cross section also we can actually find from whatever the dimensions are actually given. Okay. Yeah, I'm actually skimming through this because I'm actually not having my writing part with me. So what I actually do is I will just send this particular solution table. Okay, I will send this particular for this particular tutorial. I will actually send the solutions because I'm not having the writing part with me, so I know it is actually difficult for you to understand without my writing part. So I will actually send this solution tutorial, a solution for this tutorial, so you can actually go through that. But for now, I'm just skimming through. Okay, yeah, yeah. So once you actually get yeah, from here you can actually find what is actually the uh, uh, yeah, M and L and all those things. Okay. So here we know what is actually the Q flux. We have already derived what is actually the Q flux from the bottom surface as well as the top surface. Yeah. So therefore, we can actually find what is actually the QFO as well as the QFL. Okay. Yeah. So that is actually for a single fin. For a single fin, how much it is? That's what we were actually talking about. Okay. Yeah. But here, what is actually asked is actually the corresponding maximum power dissipation. Okay, so therefore, you can actually see what is actually the number of fins and into the QFX divided by what is actually the base area sample. Okay, so that's what it is actually going to be asked. Okay. So it is actually given maximum stack is actually of 200 wide and 100 deep. Okay, so 200 by 100 so that is actually given 200. Yeah, here it is given 200 is actually the total width and 100 is actually the total depth. Okay, so out of the 200 we can actually say that a zero point 0.1 so here it is yeah, 1 is actually the thick for each condition. Okay, so what is actually the total area taken by the fin? It is actually depends upon the number of fins. So 1 into number of fins. So that is actually the total area taken by the fin. Okay, so rest of the area, say suppose if you are having n number of fins, then the total area taken by the fin attached to the base is n into 1 Okay, that is actually the yeah. Obviously, the depth also we need to actually consider. So and rest the free area, which is actually or the non-fin area, whatever we actually discussed when we actually had this uh, fin efficiency as well as the fin effectiveness. More than fin efficiency, it was actually the uh, fin effectiveness, right? Uh, no fin area, Q fin. Yeah, okay, okay. Fin effectiveness. There is this no fin. Yeah. So this is actually the fin surface, total surface, and multiple fins. Yeah, we were actually talking about this is actually the no fin area, right? So area to which the fin surface is actually not given. Yeah. So uh, yeah, so that is actually the maximum heat power. So whatever the heat transferred from the fin plus whatever the heat transferred from the no fin area. So that is actually the maximum possible heat transfer. Okay, so as I said, the fin area we can actually find from number of fins into the thickness of the fin. Okay, into the depth, and the area or the not fin area, the area on the base to which the fin is actually not attached is equal to 200 minus number of fin into 1 thickness into 100 Okay, that actually gives us the no fin area. Okay, and we actually know that the base temperatures we actually know, and the heat transfer coefficient and the uh, ambient temperature. So that also we actually know. So from there all, we can actually find what is actually the total heat transfer from the surface. Okay, so NF into QF0, so number of fins into the heat flux transferred to the fin, transferred to one fin, plus W minus NF into T. Okay, so W minus NF into T. That is actually the into DH into 100 So that actually gives us the total number of total area. Okay, so that's how we can actually calculate over here. Yeah, here the number of fins also given us 50 fins. So all the dimensions are actually given, all the values are actually given. You have to only simply put it into that, and you will get the value. Okay, so is that clear? Um, or do you want me to explain again? Is that clear? Is it clear or
Yes.
yeah, fine. Yeah. So I know without writing this down, it is actually a bit difficult to understand. So that's why I'm just explaining and making sure everyone getting it. Okay. Yeah. So therefore, yeah. So yeah, that's how it we can actually find the maximum possible power dissipation. So maximum possible means whatever the power dissipated from the fin plus whatever from the no fin area. Okay. Yeah. So if it is actually asked you for the effectiveness and all, so then obviously you can actually calculate how much is actually going to be the heat dissipation. Okay. So for all overall effectiveness, it is actually given uh, q yeah, qt from the fin divided by the no fin area. Okay, so all those things we can actually see and you can actually calculate. Okay, q total divided by q no fin area. So q total is what we are actually calculating from over here. So q0 max divided by ql max plus ql max. So that actually gives us the total power dissipated divided by only this much, the two times. So w minus nft dh into this theta 0 for q0 max q0 as well as this term. So both these terms summation together, it will actually gives us what is actually the heat transfer from the no fin area. Okay, so therefore that actually gives us the total effectiveness. Yeah. Uh, yeah. So that's how that is how you can actually tackle for this fin problems. Okay. So we have actually discussed only two or three problems, but in textbooks you can see that many practice problems as well as the exercise problems are actually given. You can actually go through that. Okay. Yeah. So yeah. So now we are actually going to see two or three problems from the transient conduction method. So one problem you can actually see the first one, the simple problem you can actually see. Uh, Here it is actually a cooling in the space application. So as permanent space stations increase in size, there is actually an attendant increase in the amount of electrical power they dissipate. To keep a station compartment temperature from exceeding the prescribed limit, it is necessary to transfer the dissipated heat to space. Okay, so whatever the heat generated by the electronic components, it need to be actually cooled. Okay, it need to be actually dissipated to the space. So there is actually a novel idea for that. A novel heat rejection scheme that has been proposed for this purpose is termed as liquid droplet radiator. Okay, so what it actually does is the heat is actually first transferred to a high vacuum oil. Okay, so heat from the electronic component, it is first transferred to a high vacuum oil. Some oil it will be actually first transmitted, which is then injected into outer space as a stream of small droplets. Okay, yeah, here you can actually see. So here you can actually see the droplets. These droplets first it actually takes heat from the electronic component, and then it will be actually uh, put it into a cabin. Okay, so it is actually then put it into some equipment so that it is actually going to be rejected as a small droplets. Okay, as small droplets it will be actually given out, so that it is actually from here it is actually open to space. Obviously it is actually not open to space, so there is actually going to be the boundaries, but it is actually open to radiate to the space. So obviously to the space the heat rejection is actually through the radiation process only. So since it is actually droplet, we can see that surface areas are actually going to be higher and all. So therefore, the radiations, the surface areas are actually very high, and it is actually going to be rejected. The heat is actually be rejected to the space by radiation, and so it is actually traveling also. So we are actually giving a push at the inlet. Okay, so therefore it is actually being actually made into droplets, and it is actually moving with a velocity v, and by the end it actually being taken to the other end, we can see that it is actually going to be cooled. Okay, so that is actually the basic idea. The heat is first transferred to a high vacuum oil, which is then injected into outer space as a stream of small droplets. The stream is allowed to transverse a distance L, over which it actually cools by radiating energy to outer space at absolute zero temperature. Okay, the droplets are then collected and routed back to the space station. Consider conditions for which droplets of emissivity 0.95, emissivity is given, a diameter 0.5 mm, diameter of the system is given, are injected at a temperature Ti is equal to 500 Kelvin. Okay, so here the temperature is actually given as 500 Kelvin. So the droplets, when it is actually formed, its temperature is given as 500 Kelvin and a velocity v of zero point 0.1 meter per second. Okay. The properties of the oil are O is equal to 859 kilogram per meter cube. The capacity is actually given. and the conductivity is given. Assuming each drop to radiate to deep space at the surrounding is equal to 0 Kelvin, determine the distance L required for the droplet to impact the collector at a final temperature Tf is equal to 300 Kelvin. What is actually the amount of thermal energy rejected by each droplet? Okay. Yeah. So we need to actually do two things. First of all, I assume you got the idea. So droplets are actually being made. Once it is actually being made, the temperature is 500 Kelvin. Okay. So our necessity is that by the time it actually reaches over here, the temperature should be 300 Kelvin. Okay. The velocity at which we are actually pushing the droplets, it is actually given as 0.1 meter per second. Okay. Yeah. So what is actually asked first is actually what is actually the length. So what should be actually the length of our system such that we are actually allowing the radiation over this much length. Okay. Yeah. So and again it is actually asked what is actually the amount of thermal energy rejected by each droplet. Okay. So therefore, from the first from this one itself, we can see that it is actually a transient one because we are actually talking about the reduction in temperature of a particular droplet. Okay, over time. So we are actually saying that yeah, it is actually each mass of a droplet, its temperature is actually reducing from L is equal to 0 to L is equal x is equal to 0 to x is equal to L. Okay, so therefore we can actually see that this is actually a transient conduction problem we are talking about. Only that we need to actually see whether we have what type of situation we are actually talking about. Okay, so obviously the clue is that we are actually talking about small droplets. Okay, since we are actually talking about small droplets, there is actually high chance that we can actually consider that this is actually the temperature variation within the droplets. We can actually assume to be yeah, variation, the gradient within the droplet we can actually assume to be zero. Okay, so that means the droplet is at constant temperature, okay, corresponding to the temperature difference from the outside and the surface. Okay, so that's how we define the uh, lumped capacitance, right? But for that, we said that for the lumped capacitance, we said the Biot number should be actually less than zero point 0.1. Okay, so our hinge is that this is actually a lumped capacitance method, but we need to actually be sure whether we can actually use the lumped capacitance. Okay, so therefore we need to actually first calculate the lumped capacitance. uh, yeah. So here, therefore, it is actually given. uh, uh, yeah. So here the diameter is actually given, the conductivity is actually given. So we need to calculate what is actually the H associated with that. Okay. So we need to actually see what is actually the H associated with that. Uh, yeah. Sorry. Yeah. So H associated with that. So, but we know that we actually seen. Yeah. So for the lumped capacitance, so we are actually taking that H is equal to um, yeah, alpha H is equal to epsilon T raised to C into the emissivity. Okay, so yeah, emissivity is actually the alpha into sigma into T raised to 3. Okay, yeah. So this is actually the first one is actually the Stephen Boltzmann constant. That value we actually know. The emissivity we actually know. Temperature raised to 3. Okay, so H is maximum when T is actually maximum. Yeah, so H we need to actually find first. Okay, so therefore yeah, Q we actually know as a sigma T, sigma into mcvt into a into T raised to 4 minus T and infinity raised to 4. Okay, so but we said that T infinity is equal to 0. Okay, so T infinity we said is equal to 0 to the ambient surrounding. So therefore Q is equal to sigma into emissivity into area into T raised to 4. Okay, but we actually know that Q is equal to HA into delta T, right? So therefore we can actually see that here it actually comes as the H actually takes the form sigma into emissivity into T raised to 3. right? So that's how we are actually saying it is equal to H. Okay. So H is actually maximum when T is actually maximum. So therefore, we can actually say that uh, yeah, T maximum is actually given us how much 500. Okay. So at the beginning, T is actually given us 500. So therefore, putting these values, we can see that H is coming somewhere around 6.7. Okay. Because emissivity is actually given us how much? Emissivity is actually given us zero point 0.1. Okay. Alpha, we actually know it is actually how much? 5.67 into 10 raised to minus 8. Steven Boltzmann constant. So therefore, this value we can actually give it as 6.7. Okay. So Biot number, therefore, we can actually calculate at h d by k. So d is actually given as a zero point 0.5 meter or zero point 0.5 mm, right? So d is actually given as 0.5 mm. Conductivity is also given as 0.14. So inputting all these values, we can see that Biot number is actually coming to be 0.02, which is less than zero point 0.1. So therefore, we can actually take the lumped capacitance model here also. Okay. So even if it is actually given that, so the values are actually coming to be, say, Biot number coming to be zero point 0.5 or something. Okay. So Biot number is actually coming to be zero point 0.5 in this case. Suppose it is actually coming to be zero point 0.5 and all. But again, so in that case, we are actually saying we cannot actually go with the linked capacitance model if you are actually saying. Okay. So but for this droplet, a cylindrical system, it is a spherical system, it is actually going to be and all. And if you're actually feeling that it is actually going to be very difficult to analyze, say for the temperature gradient, etc., if you're actually going to take, and if you're actually saying that it is very difficult to analyze, we can actually say that you can actually write the assumption that okay, even though Biot number is actually greater than zero point 0.1, okay, and we are actually saying that still I am actually taking this, considering it as a lambda capacitance model. Okay, so if you are actually doing that, then you have to actually write uh, uh, your justification for that. Okay, so you must actually say that if I am actually going to consider it as a finite volume system with the temperature variation within and out, then the analysis is actually going to be very difficult. So therefore, I am actually considering it to be a limited capacitance, even though the Biot number is actually greater than zero point 0.1. Okay, so that is also fine. Okay. But if it is in the question, it is specifically asked that you have to actually use the finite method and all. So then you have to go for the finite method. Okay. Yeah. So as long as Biot number is somewhere around less than zero point 0.5 and all, you can still use the lumped capacitance method. Okay. If otherwise, it is actually not asked. Okay. Yeah. So you have actually seen that the Biot number is actually less than zero point 0.1 over here. So lumped capacitance model we can actually use. But we cannot actually use the conventional method. So in our lumped capacitance, what we actually said is it was actually immersed in the liquid, right? So in our condition, what we actually said is the outer condition is actually going to be h into area into t minus t infinity. Okay, so that was actually our criteria, and based on that, we actually come up with our particular equation. But in this case, it is not h delta t, but it is actually the radiation. Okay, so the basic equation is actually same. The energy balance is actually going to be the same. The rate of change of internal energy of the system is equal to the heat emitted by the system. Okay, so rate of change of energy in the droplet is equal to energy emitted by the droplet. Okay, so density we know, the volume we know because the diameter is actually given, the heat capacity is actually given. So dt by dt is equal to sigma a epsilon into surface area we actually know, and t raised to 4. Okay, this t variation, t is actually varying with the time, so that's what we need to actually find. Okay, so here it is actually simple integration. We can see that the like terms we can actually make it in the same side, and so therefore we are actually coming up with the equation. So dt by t raised to 4 integrating from 500 to 300. Okay, because we are actually saying that by the time it actually reaches from x is equal to 0 to x is equal to L, it need to be actually reduce its temperature from 500 to 300 Kelvin. Okay. And what we are actually saying is the time taken is actually from 0 to t. Okay. Yeah. So all the other values, it is actually known. So therefore, from the basic energy balance, we are actually solving into t is equal to 25.2 seconds. Okay. So t is actually given us 25.2 seconds. Okay. Yeah. Yeah. So that is actually the time taken for the temperature to vary from 500 to 300. Okay, so we actually found now what is actually the time taken for a cylinder. Okay, it's the time taken for a droplet to reduce its temperature. Okay, with the condition, with the radiation, what is actually the time taken for the droplet to change its temperature from 500 Kelvin to 300 Kelvin. Okay, yeah. So now again, it is actually given that it is actually okay. So now we have actually found the time variation. But again, we have actually seen that the velocity there is it is actually moving with the velocity. Okay? So you can actually see that the velocity has nothing to do with the radiation. The velocity has nothing to do with the heat transfer. Okay? So only that velocity is actually used over here so that it is actually moving from one location to another location. But the velocity has nothing to do with the radiation. But why the velocity is actually important is that based on the velocity we need to actually specify what is actually the total length of the system. Okay, what is actually the total length of the setup, so that the cooling will be actually proper. Okay, so therefore we can see that the velocity is actually given as 0.1 meter per second, and we actually found what is actually the total time required for the droplet to cool to the from 500 to 300. Then based on that we can actually find what is actually the total length. Okay, total length is equal to velocity into time, which is equal to 2.52 meter. Okay, yeah. So it is actually once you actually understand, or you once you actually get the concept clear, it is just a 3 or 4 steps. Yeah. So that's how these lumped capacitance models we can actually go for. Okay. And the second part is what is actually the amount of thermal energy rejected by each droplet. It is actually very simple, MCP delta T. Okay. Density we know, volume we know, and the capacity we know, and into 500 minus 300. MCP delta T, that is actually the total energy emitted by the each droplet. Okay. Yeah. So is that clear? Is that clear?
Yes, sir.
Yes, sir.
Yeah. Okay. Yeah. So that's how you can actually go for the limited capacitance and all. So in between there is actually one more question. Okay. So in the question, I'm not going to discuss it since I am actually going to send you the solution. You can actually go through that. So only that question, what it actually says is that, so in our regular transient conduction, okay, limited capacitance, we said that the ambient temperature is at a constant value of T infinity. Okay, ambient temperature it has a constant value of T infinity, and therefore we have actually made our equation T theta is equal to T minus T infinity. We said that we are actually making it, we are actually doing this assumption so that our basic equation is actually going to be a homogeneous equation. Okay, so we said that if you are actually making our assumption such that theta is equal to T minus T infinity, so H is theta is equal to minus rho VC d theta by dt. Okay, so there is actually no constant terms, and our equation becomes homogeneous. Okay, but in this particular question, what is actually asked is T infinity, the ambient temperature is equal to T0 plus A into e raised to t. So there is actually some temperature term also comes into picture. Okay, so temperature time also comes into picture. So therefore when you are actually doing you can actually see that our equation cannot is actually not going to be an homogeneous. Okay, so this is actually the basic equation. I'm sorry, so this is actually the basic equation comes into picture. Okay, so T is equal to T0 minus A into e raised to t. Okay, T0 plus A into e raised to t. So the theta you can actually give us T minus T0. So therefore, we can actually see that when you are actually reducing your equation, there is actually going to be one more non-homogeneous term also comes into picture. Okay. So once the non-homogeneity is actually there, then you have to actually solve it using the homogeneous component as well as the particular integral. It is just a matter of one more term actually comes into the picture. Yeah, so you have actually studied in your max classes. If you are actually going to have another non-homogeneous term, your total solution is going to be homogeneous part plus the complementary part plus the particular integral. Okay, the complementary part plus particular integral. So luckily for us, the particular integral is actually given as b into e raised to t. Okay, so they themselves have actually given the solution for the particular part, particular integral. It is given as b into e raised to t. So therefore, the total solution is actually going to be homogeneous part. Homogeneous part, we know it is going to be c1 into e raised to minus ct. Okay, we have actually derived that. Plus particular integral. Particular integral is b into e raised to t. Okay, so therefore the total solution. Okay, yeah. So therefore the total solution is homogeneous part c1 into e raised to minus ct. C is actually going to be equal to 1 by 2. Okay, plus particular integral. Particular integral given us b into e raised to t. Okay, so what is actually asked us is therefore we need to find what is actually c1 and what is actually b. Okay, what is actually b and what is actually c1. We need to actually find that. Okay, yeah. So that is actually the what problem is. You can actually see how they have actually solved it. For that, what they have actually done is they have actually into the basic equation, they have actually input what is actually going to be theta p. Okay, particular integral they have actually put. So from there, you can actually get what is actually going to be equal to b, and then by putting the boundary conditions, you can actually find what is actually c1, and therefore the total equation is going to be theta p plus p plus theta h. Okay, yeah. So you can actually go through that, and if you have any doubts, you can actually ask me. You can actually contact me. Okay, I know it is actually a bit advanced, but it is actually useful for you in order to get your concept clear. Okay, yeah. So that actually concludes the tutorial part. I just wanted to include one more problem from the semi-infinite method. Okay, one more problem from the semi-infinite method also I need to actually include. So that's why I just put one more problem over here. Uh, yeah. So you can actually read that. Yeah. So here it is actually given as a thick steel slab, density given, heat capacity given, conductivity given, is initially at 300 degrees Celsius and is cooled by water jets impinging on one of its surface. Okay, so the thick slab, it is actually initially at a particular temperature, and one side it is actually being cooled by an jet impinging. Okay, so here you can actually see that water is actually coming and hitting on that. So there is actually convective heat transfer going to happen. Okay, the temperature of the water is given as 25 degrees Celsius, and jet maintains an extremely large, approximately uniform convection coefficient at the surface. So here it is given as heat transfer coefficient is actually very large. Okay, heat transfer coefficient is very large. So whenever heat transfer coefficient is actually very large, you can actually consider T surface is equal to the T infinity itself. Okay, we can actually consider T surface is equal to T infinity because we know Q is equal to H A delta T. Q is equal to H A T surface minus T infinity. So if H is actually going to be very large, then the delta T is actually going to be very small. Right? Q is equal to H A delta T. If the H is actually going to be very, very large, then the delta T is going to be very, very, very small. Okay, so that's why you can actually consider T infinity is equal to Ts. Since it is actually given as extremely large, approximately uniform heat convection coefficient. If the heat transfer coefficient values were actually given, then you have to actually consider that. Yeah. So therefore, it is given as assume the surface is maintained at a temperature of water throughout the cooling. So here explicitly itself, it is actually given out here. The question is that how long will it take for the temperature to reach 50 degrees Celsius at a distance 25 from the surface. Okay. How long will it take for the temperature to reach 50 degrees Celsius at a distance 25 from the surface? Okay. First of all, you need to see, can we actually take the lumped capacitance? We cannot take the lumped capacitance directly here itself. First of all, it is actually given as a thick slab. Okay, it is actually of a very large thickness. So that actually gives us the impression that it is actually not going to. And second, it is actually given that initially it is at 300 degrees Celsius. And in the question itself, it is actually asked at 25 it is actually going to be 50 degrees Celsius. Okay, since a dimension is given and the temperature is actually given, it cannot be actually lumped capacitance. If it is a lumped capacitance, so it doesn't matter whatever the distance is going to be, everywhere it is actually going to be the same temperature. Okay, so from the question itself, therefore, we can actually see that it is actually not a lumped capacitance method. Okay, so it need to be actually either finite method we didn't see, or the semi-infinite approximation. Okay, so the clue is that it is actually given as a thick steel slab. Okay, a thick steel slab means that its thickness is actually very large. Okay, so therefore it can be actually considered as a semi-infinite method. Okay, since the clue is actually there, thickness is actually given over here, you can actually take it as a uh, semi-infinite approximation. Okay, so therefore it is actually semi-infinite approximation with a constant surface temperature. Okay, semi-infinite approximation with a constant surface temperature. Okay. So what the question is actually asked, at some location, say location is equal to 25 right? At 25 at what time the temperature is actually going to be uh, 50 degrees Celsius. Okay, so we have seen that at T1 at very low temperature, at very low time, obviously the information will not be actually reaching 25 Okay, so as the time increases, the at a particular location, the temperature is actually going to increase. Okay, yeah. So from the basic equation, we actually know that this is actually the basic equation. T minus Ts divided by Ti minus Ts is equal to error function of eta. But what is actually eta? Eta is equal to x by 2 into root alpha t. Okay, yeah. So we can actually see that all the values are actually known over here except t. So we know what is actually Ts. Ts is given as 25 degrees Celsius. T initially is actually given as 30 degrees Celsius. Do you know what is actually T? Yeah, T is actually known. T is actually given as 50 degrees Celsius. Okay. So T minus T infinity divided by Ti minus T infinity. How much is that? What is actually T? What is actually T? Can anyone calculate for me that? T minus Ts divided by Ti minus Ts. Can anyone calculate for me? Is it clear? What is actually T? What is actually T? The question it is actually given us what is actually the time taken for for the temperature to reach 50 degrees Celsius at a distance 25 Okay, so therefore in the eta it is actually going to be x by 2 root alpha t, right? So the equation is going to be t minus ts divided by ti minus ts is equal to error function of x by 2 root alpha t. X by 2 root alpha t. X is actually given as 25 Okay. Correspondingly, the temperature is actually given as 50 degrees Celsius. Okay. Ts is actually given as 25 degrees Celsius. Ti given as 300 degrees Celsius. Again, Ts given as 25 degrees Celsius. So only unknown is actually going to be the T. Right? Are you getting? Because this kind of questions will actually come for exam. Is that clear? Is it clear?
Yes, sir.
So can you actually calculate this part? Can you actually calculate this part for me? So t minus ts, how much is going to be? It is going to be 50 minus 25. That is 25 divided by ti minus ts, 300 minus 25. That is going to be 275. Okay. So that is equal to 0.09. Okay. T minus ts divided by ti minus ts, it is equal to 0.09. Okay. So, but we need to actually know what is actually x by 2 root alpha t. Then only we can actually calculate that. Okay. So, but we know that so error function of eta is equal to 0.09 now. Error function of eta is equal to zero point 0.09. So correspondingly, we need to find what is actually eta value. Okay. Yeah. So here in your textbook, it is actually given us the eta value, error function of eta, and corresponding eta value are actually given. Okay. So now we have actually found that error function of eta is equal to 0.09. Okay. So here we can actually see error function of eta is actually given as 0.09. Correspondingly, eta value is equal to 0.08. Okay. So therefore, if you come into your equation, so therefore eta is equal to 0.08. But what is actually eta? Eta is equal to x by 2 root alpha t. Okay. So in this case, we know what is actually x. X is actually given as a 25 mm. Okay. Alpha we actually know because all the properties are actually given, right? K by rho Cp. So from here you can actually find what is actually alpha. Okay. So only unknown over here is actually t. So from there, you can actually calculate what is actually the time. Okay. So that's how you can actually tackle this kind of semi-infinite approximation. Okay. So once you have this table, okay, once you have this table, you can actually convert eta into error function of eta or error function of eta to eta. Okay. Yeah. So here we have actually given for convective boundary condition also how it is actually going to be. In this particular question, if the convective heat transfer coefficient was actually given, okay, if the instead of very large convective heat transfer coefficient, it is given as convective heat transfer coefficient is actually a particular value, then you should have actually using this particular equation. Okay, so here error function, complementary error function is actually given. Okay, complementary error function is 1 minus error function. It is given over here. Okay, all the other values are actually known. H will be actually given to you, x is actually given to us. Okay, k is also given to us, alpha we can actually calculate. Okay, so therefore from here also you should be actually able to find what is actually going to be the x value or the t value. Okay, yeah, so that is actually very simple convective heat the semi-infinite approximation. From the textbook also I think some problems, exercise problems are actually given. You can actually go through that. Okay, yeah, is that clear? Is this problem clear? Okay, I assume that is actually clear. Yeah. So go through the problem. So out of 30, some 25 marks at least will be actually for problems only. 20 to 25 marks at least will be actually for problems because derivations, nothing much we can actually do. Okay, obviously, even though derivations are actually there, it will not be actually whatever we actually seen in the class. Maybe we can actually change a boundary condition for a particular problem and we can actually give you that. Okay, so you must actually go through the tutorials and you must actually go through as many problems are actually possible. Okay, yeah, so if you have any doubts in between you can actually contact me. Okay, so anything else? Yeah, so this solution for tutorial I will actually send you, you can actually go through this. Okay, yeah,
Okay, sir.
yeah, okay, okay, then have a nice day to all.
Thank you, sir.